So we ended our lecture here where we discussed the concept of energy, and it really is just the energy associated with the vector v um is like written this way. It's an inner product pero ginigitna mo yung matrix. So usually this is a symmetric matrix na nilalagay mo sa gitna. And you can show na it is positive definite kapag para sa kahit na anong vector is positive yung binibigay. Okay? And simple yung implication nito pagdating sa, syempre, alam naman natin na meron kang tinatawag na eigenvalue decomposition. Sorry, eigen decomposition of a matrix, right? And we know that something happens here. I mean, may direct implication yon dito. Kasi, for instance, if, say, x here is an eigenvector of S, and that means Sx is equal to lambda x, as you can see, for the eigenvectors, no? Like, pag sinubstitute mo dito yung eigenvectors, like, what will happen is, pwede mo siyang isulat this way, like, e pre-multiply by x transpose. So you'll end up with x transpose x. And note that x transpose x, that is never negative. And in fact, if you have an eigenvector na hindi trivial, meaning hindi siya zero vector, this will be positive. Okay? Maging zero lang siya if the eigenvector is zero. So what this really means is that positive yung x transpose S x if positive yung eigenvalues. Positive yung eigenvalue. Now, how does that relate to any arbitrary vector v? So remember yung concept ng like transformation. Like you can always think of the vector v as a some kind of linear combination, di ba? Of a basis. And the eigen vectors can serve as basis. So we've already established that. So if it is a basis, then lahat nung mga ano na to, expressions na to, diba, can be superposed dahil V can be expressed as a linear combination of the eigenvectors. And so what happens is this, yeah. Na this can only be positive if all the eigenvalues are positive. So yun talaga yung pinaka-implication. You just have to prove that the eigenvalues are positive to say that a matrix is symmetric and positive definite. That's it. Okay? I think we ended here. So and I offered some additional properties, but these are not really that useful to us right now. Okay? But yeah, are you okay with this? Yung explanation natin why just checking the eigenvalues already tells us kung positive definite yung isang matrix? Can I see reactions? Okay naman. Hello po. Sige po. Labas na po ako. Teka lang kasi may may delivery ako. Wait lang. I'm gonna pause. There's a special no. There's a special property here na we won't really prove, but this is needed for the discussion natin mamaya. So you will have to keep in mind this thing. Actually yung dalawang bagay na yun. Like let's write them here. So the first one is that if eigenvalues are all positive, then matrix is symmetric and positive definite. Okay? So very important. And yung isa pa, this is the first one. Yung next is if the matrix can be written as something like A transpose A, something like that. Okay. Then matrix is symmetric and positive semi-definite. Bakit semi-definite? Ano ibig sabihin ng semi-definite? Semi-definite is included yung zero. Okay. An additional property nito, paano ayun. Ang additional property nito is that eigenvalues, parang nagtatali yan eh. Eigenvalues are greater than or equal to zero. Kasi yun yung semi-definite na case. Kapag may eigenvalue ka na zero, then semi-definite na siya kaagad. Now, the reason for this is that it could happen na itong A transpose A ay hindi well-behaved. So ano ba ibig sabihin ng hindi well-behaved? Tungkol siya sa columns. Kasi essentially A transpose A is like what? Is really like something like calculating inner products, di ba? Para bang pag tinreat mo yung columns of A as like vectors, this is really like computing inner products between vectors. And by the way, automatic na magiging symmetric yung result nito. We won't prove that, but you can imagine na since these are really inner products, automatic siyang symmetric. Diba? Kasi yung, kunyari, sabihin natin na lumabas ay si, di ba, pwede mong isa-isahin yan. Like, kung kunyari, sinulat mo si A, kunyari sinulat mo si A na matrix as composed of vectors na nakatayo. So let's say this is A1 and then A2, di ba? Kung yan yung notation natin and then up until AN. Then pag lumabas si A1 transpose A3, for example, magiging equal lang tong inner product na to sa A3 transpose A1. So you see, this gives it symmetry. So A transpose A is guaranteed to be symmetric. It's just that kailangan mo na lang tignan yung kanyang pagiging positive definite. And sabi nga natin ay positive semi-definite. So to answer this question na why must columns be independent, essentially, this is about the energy. Kasi kapag hindi independent yung columns, yung kaninang energy natin na pag binigyan mo si S ng any vector V, di ba? Tama? Pag hindi independent yung columns ni A, it could end up that this energy calculation becomes zero for some vectors. And what are these some vectors? Well, these some vectors are like kapag may linear combination ka kasi nung kapag hindi siya independent, kunyari let's say si AN, depende siya dun sa mga ibang vectors. Then kahit na anong coefficient yung mabigay mo dito kay AN, something like that, if you think about it. Any coefficient na mabigay mo dito kay AN ay magiging magi-GG, kumbaga. Kasi dependent nga siya dun sa ibang vectors. So hindi siya mag-contribute ng anything new. So you will end up having say zero na energy for that. And to further illustrate that, kasi baka sabihin nyo, anong relationship niya nun sa V transpose SV? Well, remember, we have the condition na if S is can be written as A transpose A, di ba? Ito yan. If S can be written as A transpose A, So it's like saying that this is like V transpose A V. That's our rule for this discussion. So it's like saying this is AV. So you see, this is AV, and etong ano ba tong V transpose A transpose? It's really like AV transpose. Tama? So it's like the inner product between AV and AV. Diba? Parang inner product of AV na vector with itself, right? And now you have a problem if hindi hindi linearly independent si A. Kasi kapag hindi siya linearly independent, may mga unreachable ka na 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 spaces, di ba? Like yung column space mo, yung column space ni AV is not gonna be full, parang ganun. So that's the issue here. Okay? Anyway, I have a few examples here which I won't try to demonstrate. So I'd like you to go home. Well, you're probably some of you are probably home. I'd like you to maybe do these exercises na lang just to show na nag-hold itong um requirement na to na kailangan independent yung columns para maging symmetric and positive definite. So what you can do there is that look at A, all right? The nice thing here, by the way, is A need not be square. Kasi automatically, yun, pag ginawa mo si A transpose A, magiging square siya. So kaya makita nyo dito sa example natin, A is not square, right? This is 2 by 3. And dito sa second example, A is 3 by 2. Okay? So yeah, for instance here, like you'll just have to look at A and see, teka, is this a linearly independent set? Like yung mga columns niya? So let's answer the question, like is S is which is going to be A transpose A, is it going to be symmetric positive definite? So what do you have to answer first? Like, does it have independent columns? So okay, this is very important. So kapag hindi nyo na yung ganito, kaya ako sinasabi na pati yung mga nauna nating lectures, kahit hindi sila directly covered nung midterm, kailangan yung naaalala sila. Kasi without remembering or without knowing how to show independence of columns, you cannot answer this question. Well, but then you brute force, though, like to get this and then look at its eigenvalues, but it will probably take you more time than is warranted. Kasi kung kunyari, ito yung tinanong ko talaga sa inyo at sinabi nyo lang sa akin, A is like independent. The columns of A are independent. And so S is symmetric positive definite. Tapos na, 'di ba? Kasi sinabi ko na sa ano yun sa as a fact dito sa ating notes. So let me ask you, are the columns of A independent? Can I see hands? If yes, thumbs up. If no, cross. Okay. I want to see your answer. Everyone should answer. Like, thumbs up. May isang cross. Who said the cross? And what made you think the cross? Because most of you said thumbs up. Can you sense a chat or just speak up? Like your reason? Okay. Column 1 plus 2 po. Oh, what do you mean? Like, are you saying that column 3 is column 1 plus 2? Is that it? Sorry daw, mali daw pala. So, what are you saying here? Magpapalit ka ba ng sagot? Linearly independent na lang ba? So, what is it? Independent daw. Okay. Unfortunately, mali kayo lahat. So, bakit? So, please, let's look at this. Okay, may nagsabi sa inyo, sabi, column 3 po is equal to -1 of column 2 plus twice of 2. But that's not really the way to go about this. Like, it the point here is not to compute, okay? Not to show me na column 3 is blah blah blah. Remember, this can be answered like conceptually. Like one look lang dun sa matrix, dapat alam nyo kagad na hindi na posibleng maging independent yung columns. Bakit? Kasi ano ba yung column? Ano yung pinakamalaking column space nito? The pinakamalaking column space nito is, sabi ng isang classmate niyo, yes, R2 ang column space. So, ilang ilang columns lang yung kailangan mo for I mean, at most ilang columns yung dapat na meron ka to establish linearly independent yung columns. Kung R2 lang yung kaya mong puntahan, what? Kailangan dalawang vectors lang. Meaning, si 1, 1, let's say ito si, sorry, it's not 1, 1. Si 1, 1, let's say ito si 1, 1, and then si 1, 2, let's say ito si 1, 2, so I'm drawing it to scale, sapat na yan to be a basis. So ano si 1, 3? Si 1, 3 na sabihin natin, nasan ba siya? Sorry, this is not to scale. Nagkamali pa. Ito pala si 1, 2. Tapos si 1, 3, hindi nyo kailangang i-prove sa akin na 1, 3 can be written as a combination of 1, 1 and 1, 2 because it is obvious that this vector here doon sa basis, like pag nag-draw kayo ng coordinate system na ganyan yung basis, matatamaan nyo yung point na to. So there is a representation of 1, 3 in terms of 1, 1 and 1, 2. And that's it. Just by seeing that the column space is R2 and your source vector space lives in R3, may problem ka na kagad dun. I don't even need to proceed. Like, immediately I say, oops, hindi to linearly independent kasi column space is R2 and I have 3 vectors. Is that clear? Can I see hands? If it is clear na mali yung sagot kanina. Okay? Okay? Good, good, good. So let's look at the second question. Let's look at the second. Ano yung sabi sa second question? Yung A naman daw, ganito naman yung tsura. What is this? 1, 1, 1, 1, 2, 3. Now let's ask it again. If we define some matrix S as A transpose A, is it going to be linearly independent? Is it going to be symmetric positive definite? What about it? Can I see hands ulit? Thumbs up if yes, cross if not. Thumbs up. Thumbs up, thumbs up, thumbs up. Yes, exactly. Sabi ng classmate nyo, since ang destination ninyo, ang largest, no? Ang largest space na pwede nyo puntahan. It's not necessarily the column space, okay? Reminder lang, hindi it's not necessarily the column space. But the destination space is R3. And we only have 2 vectors. So the column space is actually smaller, no? Column space is smaller than the destination because it's going to be a plane. It's a plane built by this vector and this vector. It's going to be fine. Like you can immediately say na, oh, this is linearly independent from this, and then I'm done. They are linearly independent, then this matrix is symmetric and positive definite. Yun na yun. And in fact, you can like do it yourself. Like you can let me start working out this matrix S. So A transpose is 1 1 1 1 2 3, and A is 1 1 1 1 2 3. So what it's gonna end up with, so let me do this quick. So it's gonna be 3. So please confirm if what I'm writing is correct. And call me out kapag may namali akong sulat. So this is gonna be 3. And then we have here 6. And we have here 6. And we have here 14. Is that correct? Ito yung lalabas na S? Did I write it correctly? Anyone? Thumbs up daw? Tama naman daw? Okay. Good. Tama kayo. So this is the correct matrix S. And we don't even need to compute the eigenvalues at this point. We've already established that this is positive definite, whatever was formed. Okay. By the way, the point here is A transpose A is at least positive semi-definite, meaning yung kaninang problem will lead to a zero eigenvalue at some point. So yeah. Okay. There are other like ways to say that matrix or a symmetric matrix is positive definite, but we won't prove them. And these are really like parang auxiliary. Ang pinaka-important sa akin is this and the one about the eigenvalues. Okay? All right. So now actually eh, we've been dealing with square matrices. Now, what if our transformation matrix is not square? Or you don't even have to think about it as a transformation matrix. Kunyari, may data kayo na doesn't look square. And you have a lot of data like that, no? Most data are like that, I would say. We won't see square data sets. It's usually like you have a few features, kunyari, height, age, weight, and then you have a lot of patients or examples. So you have 1,000 patients with height, weight, and age. That is not square. That data set is not square. So mas madalas nyo itong makikita actually. So now pupunta na tayo sa mas practical na na world kasi originally the eigenvector eigenvalue stuff that we've discussed, they're only applicable sa square matrices, and granted they are very important in engineering. Like you'll see them everywhere. You'll see them in chemical engineering, mechanical engineering, like civil engineering, everywhere, computer science, everywhere. But the point is like square matrices lang siya nag-a-apply. Now, what if you have a non-square matrix? For example nga, the A matrix is 1,000 by 2. By the way, 1,000 by 2, this is like para kayong nag-spreadsheet. Sanay na sanay naman kayo sa spreadsheet, 'di ba? Sa Google Sheets or Microsoft Excel. You have, say, age, and then you have height, and then you list like 300 children, and then you see this data. Like if you plot it, right? You see this data. If your axes are age and height. Okay. Now, given everything we've learned, I'll tell you an important thing about this data matrix, and that is about its rank. Okay? This matrix is what we say at most rank 2. Bakit siya at most rank 2? Kasi diba, rank is only dependent on the smaller of the dimensions. Kung m by n ito, which one is smaller, yun yung kanyang magiging ceiling ng rank. Okay. Now, the reason why this part here is important is because like yung rank is like what do I call this? Yung rank is really about say how many independent no coordinates. If you think of these are coordinates like age and height, how many independent coordinates are needed to describe any point dun sa data set? And it turns out like here for every example, if you treat each example as as an example, it has its age and height kasi sila nga yung features. So the coordinates of this point are defined by ano yung scalar na minumultiply mo kay age, ano yung scalar na minumultiply mo kay height. That's essentially it. So kung ang height and age mo ay canonical, kunyari canonical basis, then sure, like whatever the point, the numbers you put here, that's it. That's gonna be your coordinates. Now, dito sa ganitong like matrices, well, we can do a lot of things. Well, one of the things that we've discussed was k-means clustering. So just reminding you na we've gone through k-means clustering, and it's already very useful. Like you can have a data set and then cluster them into groups, and you know the basic algorithm for that, and you know how to use NumPy, not NumPy, scikit-learn a little bit. You know how to use scikit-learn to do k-means clustering, so you can separate them into clusters. Okay, so sure, it's already very useful, but still maybe we can do some more. Now, may classmate kayo nagtanong sa chat, yung rank daw ba ng column space is equal to the row space? Ang answer dito is yes. Row rank equals column rank. Kaya isa lang yung name natin sa kanya, rank. Kaya nga, depende talaga kung alin yung mas maliit, yung number of dimensions. Mas marami ba siyang rows kaysa columns? So kung alin mas maliit, yun yung parang nagiging limitation mo, essentially. Para bang there's no free lunch here. Like if your row space is 2-dimensional and your column space is 1000 dimensional, then from a 2-dimensional row space, you can only get somewhere, diba? Meaning when you do the transformation, then at most 2-dimensional lang in the 1000 dimensional space yung kaya mong i-reach. So you cannot get any additional like information if this is what you're seeing. Okay. Now, when we did this k-means clustering, let me ask you a question here. May napapansin ba kayo doon sa mga clusters? So I want to see answers here sa chat. Ano napapansin niyo doon sa mga clusters? Like just observation as uh Someone said may center sa bawat cluster na mas mataas density ng points. Okay, okay. Meron dang somehow parang center, di ba? Yeah, in fact, naalala nyo yung algorithm natin ng k-means clustering? Di ba? We're really specifying na kunyari, we did 3 k equals 3 na k-means clustering dito. We are specifying that there are 3 centers, right? Na each center will represent or will parang have congregation around it. So definitely what you said is gonna be true. But any other observation? Clusters are not the same size. Yeah, it could happen. Like, 'di ba, 300 children ito, it could happen na iba-iba yung number of children. Okay? That's good. Someone said walang overlap sa clustering. Yeah, sure. Dito sa example na to, it seems like wala tayong overlap. And yes, essentially, pag nag-clustering kasi kayo, para kayong essentially para kayong nagdo-drawing ng mga circles or ellipses. Parang ganun. Nearly circles or ellipses. So parang nagkakaroon ka ng uh, like division. Someone said there is an invisible line between the 3 regions. Yes, essentially what I've also described na para kang nagkakaroon nga ng ellipses. So itong mga ellipses na to may hindi sila mag-overlap and so on. Other observations? Wala na? Okay. Ayun, sabi may center among the clusters. Yes, yes. Yun nga, nabanggit ko nga na that's essentially what k-means does. It finds centers. Um, what I'm really like was hoping to get from soliciting that is like, let me transfer it here briefly. Um, what I was hoping for was, sure, meron kang center na makukuha, di ba? But think about this. If let's say yung cluster is, let's say for this cluster here, you subtracted the center. What's gonna happen is like, para kang magkakaroon ng coordinate system that looks like that, di ba? Likewise, ganun din dito. What if you subtract the center, perhaps may ganyan kang coordinate system. You see what I mean? So, now what? Kung we're able to do that and we're able to look at the data set, given that meron kang ganyan, another thing that I was hoping you would say is there is something about how they are shaped. Like, you see, etong mga numbers na to, parang they look like an, I mean, there could be, I can put some kind of an imaginary ellipse that looks like this, no? Another is dito, may imaginary ellipse that looks like this na not really covering all the points, but I would say covers most of the points. Like dito rin, parang may imaginary ellipse. And there is a difference between how they are spread based on those ellipse. Kasi kung mayroon kang ellipse, say, kunyari, yung ellipse mo dito is mas manipis yung width kaysa dun sa ellipse na nandito, di ba? Which is mas makapal yung width. Then that is something that you'd also like to know. So far, okay naman ba tayo dun sa um, what I was looking for na observation sana? Or is anyone gonna ask, why is that gonna be important? Or do you have questions about that? Yeah. Yeah. Okay. Let me tell you about that. Yung if it is if it really is gonna be important. Okay. Now, um, if for some reason lahat ng points meron kayong coordinate system, and if for some reason lahat ng points ay naging ganito yung distribution. So I'm making it obvious here. Okay? And you did the same analysis, like, okay, let me find the center. So the center is here. So it's like I'm gonna look at a world where naka-center siya dyan. So I don't care about the original coordinate system. I just shifted the center. Isn't it important to you to know what this line is? Is it important? Can I see hands? Like as engineers, as scientists, what is this line gonna be representing? Like, so ang dami mong data, meron kang hundreds of data. What is that line gonna represent? That line is gonna represent some kind of what? Can you see answers to chat? Someone said regression, trend, regression line. Yeah, but more than like I don't want you to think about this as because regression is a huge word actually. Like when we get down to the details of what regression is a huge word. But I'm looking for a really simple word here. Someone said relationship ng x1 and x2. Perfect. Because there could be a relationship between yung coordinates na to, di ba? Granted, they are shifted. Like sinubtract mo na yung center so that na-shift yung inyong coordinates. But it's like saying that there is a general relationship between the two, right? And if I am able to capture this relationship, then nice. Diba? Like, because if you're able to capture, because this is just going to be a line, right? It's going to be a line. And not just a line. Like, if you think about it, if you are looking at this thing as yung nagsubtract ka na, you look at that and you call that, say, a subspace or a space, then that line is a subspace. And it's like saying that, oh, wait, I have a subspace that is like really, really dominant that explains my data, right? So you see that thing is important. And this is readily extensible sa higher dimensions. So for example, let me show you another example here. So suppose you have this MNIST database where these are 28 by 28 grayscale images. And what this means is this data set is rather large. In fact, I want to ask you, ano kaya yung shape ng data matrix? Like you can condense all of the information. These are just examples, by the way. These are like 25 examples in that database. We have 60,000 examples. Like people actually wrote the numbers and then nirecord yun in grayscale. And that whole data set is just a matrix. What is its shape? You tell me what the shape is. Kung yung kanina natin data set is 300 by 2, dito, what is its shape? Anyone here? Like how can I represent? For instance, each example, how can I represent this? How many features do I need? Yun na lang muna. Someone said 10 features. Someone said 0 to 9. Well, you're getting ahead here. Remember, we're computers. We're not people, for example. Like a computer sees this, he's not gonna tell you na, oh, it's a 5. So my features are, kunyari, 0, 1, 2, 3, hanggang 9. And then lalagyan niya ng score na, oh, this is 100% a 5. So sasabihin mo na 1 sa 5, 0 yung values ng features na iba. It's not gonna work like that. So what is it? So some of your classmates said 28 by 28. And that is correct. A computer sees this as a 28 times 28. Oh, how much is that? Gano'ng karami yung 28 times 28? What? I don't know how much that is. Sabi yung classmate nyo ay 784. You have 784 features. Kasi bawat pixel dyan is gonna be a number from, kung digital to, okay? It's gonna be a number from 0 to 255. And that is for, how many bit was that? That's 8-bit. So for an 8-bit data, this is gonna be 0 to 255. Tama ba? And ganun rin sa susunod na pixel. Ganun rin sa susunod na pixel. So you like to for a computer to interpret this is really a vector na 784 yung features. And if you write this sa Excel, you will probably write it as something like 7,000, 70,000, sorry, 60,000 examples. So 60,000 rows by 784. See? And what is its like highest possible rank? Like if everything was nice, its highest possible rank, let's call it R max, for example, is 784. Again, it's really just looking at the smaller number of the two. So the highest possible rank is 784. But think of it this way. The rank is really some kind of like an indication of how many, like how many unique, no, how many unique like features um can you extract from the data. So what we are really saying here is that if it is of maximum rank na 784, it could happen that really for a computer, it could happen that all of these pixels are very important. That knowing what the number, what the magnitude of the pixel here, like at this location versus this location versus this location, this location, this location, knowing those values completely is important. That's what we mean by 784 na rank. But really, we know as humans, how do we do this as humans? We look at the example, and for some reason, we are really, really good intelligent machines. We are not artificially intelligent. We are actually intelligent. So really, really good intelligent machines that, oh, that's a 5. Huh? Sabi mo, oh, that's a 2. Oh, that's a 3. There must be something there. Like there must be something in the way the pixels are lit. Like kung nasaan yung mga white, kunyari, there must be something na the way that they are lit informs us of something, some grouping, di ba? Some grouping that is rather small. Kasi dito, ilan lang yung, kunyari, pag tinignan natin bawat isa, like, meron lang tayo, tama yung classmate nyo kanina, actually, sabi niya, sir, ano lang yan 10 features lang yung kailangan mo eh. Well, sa totoo lang, you are actually trying to do that. Like, you are doing that as an intelligent human, na para bang meron ka lang hinahanap eh. Para masabi mong 9 siya, there's a specific combination of the pixels that tells you it's a 9. Sure, you can probably compute it with a 4, but if you see something, like if it is a 4 na merong bar sa taas, it's probably a 9. So you see, even if the maximum rank of this data matrix is 784, what's really useful is some combination of those vectors, di ba? So you have this vector na 784 yung elements. So it's a very tall vector. Well, dito nakahiga yung data natin 60,000 by 784. But what I'm saying is, for each example, you have 784 numbers that describe it. Essentially, what your brain is doing is that those 784, it doesn't even matter. Like, if you see a number, like, kunyari, nakikita nyo tong 6 na to, even if I represent this using raster, meaning yung pixel by pixel, if I represent it as a I don't know, 1000 by 1000 image, or 20,000 by 20,000 pixel image, you will still tell me that it's a 6. It doesn't matter, like, kung gaano siya kataas na resolution, you will tell me it's a 6. And really, what you're trying to do here, like, you're trying to teach the computer to say na, well, from those 784 pixels, why don't you extract information from it, and maybe, I mean, you can probably like reduce that to 10. Like, you only have 10 things that you're looking for. There is a specific shape for 0, I guess, or a specific shape for 2, specific shape for 1. And once you see that shape, and that shape is going to be some combination of vectors. Like, in the linear algebra world, it's going to be some combination of vectors. Then you can bin it. You can classify it. So this task is called classification, which is a classic classification is a classic task in machine learning, or we call supervised machine learning. And what if you can do something with the data to perhaps explain it better? Like, baka, I don't know, baka there is something there that allows you to classify it into 10. Like, it's like saying, now once I know the 784, I can map it to 10. And yun yung heart nung what we're gonna try to do now, which is it possible to decompose general matrices? Because if it is possible to decompose general matrices, then probably meron lang akong important aspects of it. Like, in the case of in the case of eigenvalues and eigenvectors, kunyari, 'di ba, meron kang, say, 5 by 5 matrix. Very simple. So you have 5 eigenvectors, right? Maybe some of those are more important than the others. Like, for instance, if it is a transformation matrix, so you have a matrix A, no, that transforms a matrix X, right? And let's say A is dinecompose mo, ginawan mo siya ng eigen decomposition, so you were able to get something like X um, lambda X inverse, right? And di ba sinabi natin dati na it's really like looking at the dimensions, or looking at the space, sorry, the space that A admits and the space that A throws out, kasi square naman siya, so it throws out in the same space, R2 to R2, R3 to R3. There are important ones. Like if it turned out that the lambda is just really like 1, 1, 1, 1, and so on, then that lambda must not be, I mean, those vectors must not be important, because even if you're able to compute vectors, yung ibig sabihin ng lambda is equal to 1 is that once you transform this, is that yung component niya along the eigenvector is not going to change. So why don't you forget about it? Diba? Parang ganun. There are probably more important vectors. Like if one of the eigenvectors has comparatively, no, has an eigenvalue of say 50, no? And yung the rest is 1, 1, 1, 1. Then evidently this eigenvector that has an eigenvalue of 50 is very important, right? Kasi once it gets transformed, oops, yeah. Once the X gets transformed via going through A, then yung axis mo na may 50 na eigenvalue biglang mag-shoot up. Does that make sense? So what it doesn't seem like we can do eigenvectors, eigenvalues here, but the question really is, if it was not a square, kunyari m by n siya, can it be decomposed? Because being able to answer this, no, being able to answer this will let us move or inch towards yung question ko kanina, like how do you derive patterns out of data? Because patterns are, I would say, low dimensional. Like they don't rest in this 784 dimensional world. Patterns are perhaps in 20 dimensions or 10 dimensions even. Like if you can really immediately classify na this is a 2, this is a 1, and so on. That is a small subspace. So, dun tayo pupunta. Okay. For now, okay ba tayo? Can I see hands if understood the motivation here and why we're trying to decompose a non-square matrix? Yeah. Okay, good. Good. So, here goes. This is going to be how do I say this? Uh like sunod-sunod tong mga dadating na concepts. So I'd like you just to hold on, and a lot of things are gonna be new to a lot of you. So just take note of the those highlighted in blue. Those are really important terms. Okay. Now, here goes. Any matrix A, okay? Let's say hindi siya square. Kahit square siya, okay lang. But any matrix A has what we call singular values, okay? And something called left and right singular vectors. So right now it doesn't make sense to have why do we call them left or right, but it will make sense quickly once you see the equations. But yung gusto kong i-take away nyo dito is that kung ang mga square matrices ay may eigenvalues and eigenvectors, any general matrix has singular values and corresponding singular vectors. Okay? The crucial difference here really is that meron tayong tinatawag na left and right. Meaning, for each singular value, meron kang dalawang singular vectors. Those are called the left and right singular vectors. And this actually makes sense because if you think about it, Square matrices don't need this. Bakit? Square matrices are what? Square. So, yung dimensions nung destination nila at nung source nila ay the same, right? And what happens there is that yung left and right singular vectors nila supposedly ay nagiging iisa na lang, and that is the eigenvector. You see here? Yung relationship. But if you have a non-square matrix like ganyan, then for each singular value, meron kang representation dun sa destination, meron ka ring representation dun sa source. That's what we mean here. Okay. So it looks like this. As in, I would say this is the single most important takeaway ninyo dapat. It's a mouthful, but if you read it again and again, uh, you'll get there. Hindi, joke lang. Kung mapansin niyo, kamukha siya nung ating definition ng yung equation natin for eigenvalues and eigenvectors, right? It's just that pinalitan natin ito ng v instead of just x, at pinalitan natin ito ng u instead of just x. And ito hindi na lambda, instead it's sigma. And this is just really a change of terminology because we have a change of concept. But very, very analogous yung dalawang yun. Singular vectors are analogous to singular values are analogous to eigenvalues, and singular vectors are analogous to eigenvectors, just that you now have a distinction between the right and the left. Now, why is this called the right singular vector? Well, because ganito nyo siya tatandaan, okay? Because it's like saying that you're multiplying it on the right of A to yield yung other singular vector scaled by lambda. And that's just it. Yeah. What will happen, mamaya mapapakita ko tong other way to write it. But what will happen is this. How do you say this? Let me think about it. Paano ko sasabihin? Hindi. I-spoil ko na lang kayo. Ipipilit natin, okay, na each singular vector is what we call orthogonal. Orthonormal. Meaning, if u is a singular vector, then u transpose u gives us equal to 1. Something equal to 1. This is one of the rules. Kailangan normalized siya. So each individual u's are gonna give us equal to 1. It's also the same with v's. Like v transpose v is gonna lead us to have something like equal to 1. But remember, di ba, meron tayong correspondence. Naalala nyo yung numbering natin sa eigenvalues? We have eigenvalue 1, eigenvalue 2, and so on, so on. So forth, may ganun rin tayo. We have a number of singular vectors and may correspondence yan. So for each singular vector, meron kang singular value. For each singular value, meron kang right singular vector and left singular vector. So that also means na meron tayong numbering. Like we have something like u sub 1 na syempre kapag in-inner product mo with itself, since it is normalized, this will give you 1. But if you do u sub 1 times u sub 2 na inner product, now ano na siya, no? Like different left singular vectors na. But still, they are both singular vectors. Yung isa pang magiging requirement natin dito is this should be 0. Meaning, the set of all right singular vectors is an orthonormal set. Likewise, the set of all left singular vectors is an orthonormal set. Okay. All right. Yeah, yeah, sige. Spoil ko na kayo ulit. Because of that, para lang maging malinaw na yung concept ng left and right. Because of that, if this is satisfied, you see, if we do an inner product of this with u, meaning magiging u transpose siya on the left, it becomes u transpose u and cancels to 1, and you have this really pretty equation here. And dito obvious na well, it's like left multiplying a vector to the matrix, but remember when you left multiply a vector, it is customary for you to transpose it. Pahigain mo, di ba? And when you right multiply a vector, you have it on the right as is. Okay, that's why this is a left singular vector, this is a right singular vector. That's it. Are you okay with this so far? Definitions. Can you see hands? Okay. Oh, my heart. Bakit ka my heart? Siguro alam mo na to dati pa. Okay. Sige. Anyway, now, yeah, I don't really like using this, but I get a laugh out of this term from the students, so they tend to remember it better. So, ang tawag natin dun sa singular values tsaka yung kanilang left and right singular vectors, tawag ko sa kanila ay thruple because they always come in threes. Like, yun nga, sabi ko may indexing ka, di ba? 1, 2, 3. They're a thruple. You cannot do anything about that. Okay? Very important. Kasi, di ba, ang eigenvalues and eigenvectors, ano sila? Couple lang. May, per each eigenvalue, may isa kang eigenvector. Something like that. I mean, ideally, sa mga symmetric positive definite matrices, right? Yeah. This is what I said just now, just to illustrate to you what happens when you left multiply blah blah blah. What this means is that the singular vectors are normal. Okay? I don't know what, hindi ko malalam ba't ko ginawa itong, yeah, this should be not be gold. Kasi nilagay ko lang gold pag I introduce a term that you don't know yet. But you know what normal is, di ba? You know na ang unit, ang magnitude of the vector is 1. Okay? And this is what I showed you earlier. These are its relevant forms. You can also do this thing here. Like if you transpose this, put it on the right hand side. Teka. Sorry. This is a typo because this should be 1 over lambda, okay? Yeah. 1 over lambda. Anyway, so since sabi nga natin kanina, you have some kind of a thruple. This is what happens. For a rank R matrix, so this is important, okay? Because A, if it is, even if it is M by N, its rank can be less than either of the two, di ba? Swerte na tayo, I mean, best case scenario na kung yung rank, well, very informative yung matrix, yun na lang yung sasabihin ko. If the rank is really equal to one of these two. But if your matrix is rank R, then ito yung sinasabi kong thruple, right? You have the left and right singular vectors of sigma 1, and mag-proceed yan hanggang umabot ka sa R, which is the rank. Okay? You have R number of thruples. Now, again, this should be, I'll change this before I send you this these slides. These singular vectors, by the way, the sets, okay, are orthogonal. Okay. This does not mean, I'll also revise the way this is written. This does not mean that V1 is orthogonal to U1. Okay? Because that is not necessarily true. What I mean here is that V1 is orthogonal to V2 is orthogonal to V3. So that's what I mean by kaya ko nilagyan ng subscript, okay? So please don't mistake this as saying na yung left and right singular vectors are orthogonal to each other. No. Lahat ng mga left singular vectors orthogonal sila sa isa't isa, lahat ng mga right orthogonal sila sa isa't isa. But remember, this kung hanggang rank R lang. Remember, rank R can be less than either of the two, right? So it's not necessarily true that you can complete, no? You can complete the space. Kasi, so let me illustrate this. You see, you have here, let's say this is your A. Kunyari, nakahiga siya. This is M by N. Okay? So, ang destination space mo is mas maliit na dimensions kaysa dun sa source space. But as I've said earlier, yung R, it is entirely possible that the actual rank R is less than M, which is also less than N, diba? So this is smaller. Okay? So, you might be inclined to say na okay, naintindihan ko na, sir. Kung R yung rank, then that means all of my thruples can only reach R. And remember, yung ating U na vector, yung left singular vector, it's really about this space here, 'di ba? Yung destination mo, yung U will live in that destination space, which is in what do we say this? Which is in RM. Okay? You will live in the destination space, but meron ka lang R number of unique na U. So your set is gonna be U1, U2, and so on, hanggang UR. Eh, sabi nga natin, R is less than M. Meaning, even if I collect all of these U vectors, I will not complete the space. Right? The span of all of these U vectors hanggang UR is not equal to RM. Meron kang mga parts ng RM na hindi mako-cover nitong U1 hanggang UR. Doon papasok yung augmentation na to. So, tingnan nyo to. Like, kunyari, ito. Ito yung augmentation natin dun sa kind of, to call this, sa world ni U. Di ba? So, sa world ni U, which is about yung sa destination space, ang row space mo is gonna be up until UR. So, para makumpleto mo yung space, null na yung remaining. Does that make sense? Like, meron ka pang mga natitirang mga U's hanggang umabot ka kay UN, but all of these are actually part of the null space. Sorry, the left null space, rather. Dito sa, kita nyo dito sa equation na to. These are left null space. So, at this point, like, you will have to review yung concept natin about the four fundamental subspaces, di ba? So, kung yung row space is gonna be completed by all of the U's, okay? Then, yeah. Then, yung remaining na part na untouchable, okay, must be, baliktad pala to. Dapat hanggang UM, sorry. Yeah. Yeah. So, yung remaining na part na untouchable, kailangan punuan nung null spaces. So, ganun rin yun dito kay V, no? Hindi kayang i-cover, I mean, possibly kapag mababa nga yung rank, hindi kayang i-cover ni rank R yung buong n-dimensional space na pinanggagalingan. So, si V ay kakailanganan mo pang punuan hanggang Vn. Ito typo to, dapat hanggang UM. Okay? So that's yeah, that's the thing. Okay? Okay. Hopefully mas magiging clear to as we go. But actually, let me go through hanggang ma-define na natin yung decomposition. Yung next na gusto kong i-emphasize rin dito is that unlike sa mga square matrices where the eigenvalues can be negative, right? If you have a non-square matrix like here, m by n, it is guaranteed that all of the singular values, no, are gonna be positive. It is guaranteed. Well, sige. That's actually wrong. It is not guaranteed that it will be all positive, but non-negative. It's guaranteed that they will be non-negative. I will also revise this, but what is essentially going to happen is that the singular values can only be up until R. So kung mababa yung rank, positive yung mga singular values up until the rth singular value, and then the rest of the singular values, which are gonna complete up until whichever comes first, like up until m or n comes first, yung matitira na yon, magiging zero na yung values ng singular values doon. So para bang yung mga singular values corresponding to the null spaces, kasi diba yung sabi ko yung null spaces yung kakailanganin para punuan. Okay? Yung mga singular values na to, parang patay na. Patay yung mga vectors na yon. Zero ang kanilang singular values. Ang buhay lang ng mga vectors ay yung mga up until rank R. Okay. So, recall, naalala nyo yung ginawa natin sa square matrix where we summarized everything, like lahat ng eigenvectors, sinummarize natin sa matrix X, tinayo natin lahat sila, mga eigenvectors. Likewise, we can also summarize that sa ating sinulat na equation. So instead of small v, we put big V where we put columns. Yung mga columns mo dyan ay yung mga right singular vectors. Likewise, ganun din kay U. Mga columns mo dyan ay mga left singular vectors. And itong sigma matrix is just gonna be a diagonal, no? Now, well, it's not really just gonna be a diagonal. Meron siyang, makikita nyo shortly when I write this ng mas expanded, makikita nyo shortly na meron siyang mga zeros. Kasi nga, tinan nyo yung mga shapes nito, we have AV, di ba? Where ang mga shapes nito ay M by N. Okay? And si V, ano yung sabi natin kay V? It's gonna be N, yung kanyang number of rows, which yung dimensionality ng mga vectors, by N. Meaning, kakailanganin mong kumumpleto ng N vectors. Kahit na ang rank mo is much less than that, okay? Ang sabi ko nga kanina is pupulutin mo sila from the null space. So, meron ka lang mga vectors na important, which is the first R, singular vectors, and then the rest ay pupulutin mo na dun sa kangkungan mo, which is the null space. So yun yung n minus r vectors na kukumpleto nitong matrix V. Just to make it like square, okay? And what that means really is that yung right-hand side, you have U here, di ba? Kung si V ay n by n, di ba? Si U ay tungkol siya dun sa destination space. That means this is gonna be M by M. And as I've said, likewise, kanina, like, pupulutin mo rin sa, sa kangkungan yung mga natitirang vectors niya. So, kung kunyari R is less than M, like, yung remaining M minus R vectors, manggagaling sa left null space. So, ano yung dimensions ni sigma? Di ba? So, kung ganito pala siya, like, anong itsura nung sigma matrix? So, imagine nyo, para masatisfy natin yung mga shapes, if this is M by N, and ito ay N by N, okay? Then that means, kung ito ay M by M, dapat si sigma ay M by N. Which doesn't make sense kasi, di ba sabi mo, sir, may sigma ka lang na hanggang sigma R, di ba? So, sigma 1 hanggang sigma R. Bakit magiging M by N yan? Okay? Again, the reason for this M by N at mukhang hindi na siya kayang maging diagonal, di ba? Lalo na kung yung shape ng inyong matrix ay ganyan. Paano pa yan magiging diagonal? Di ba? So, nandito yung secret niyan. Ang mangyayari is yung diagonal mo mula talaga dun sa pinakauna is mapupunuan. Okay? And then the rest ay zeros. Okay? That's what's gonna happen. Now, even dito sa parang submatrix mo na square, it's not guaranteed na lahat ito ay may entries na non-zero. Kasi 'di ba sabi nga natin, if R is less than M, then may mga entries ka dyan na zero. Kasi wala silang, hindi mo sila kailangan. So, to summarize, ganito yung itsura niyan. Kita nyo to? Meron kang N number of V's and meron kang M number of U's. And yung dimensionality nung dalawang yan, V is in Rn, para maging N by N ito, magiging square ito. U is in Rm, magiging square din ito. Now, ito ay magiging rectangular and sabi ko nga, posible ka pang magkaroon ng sobra-sobra na zero, pero best case scenario, if very, very sulit na sulit yung matrix ninyo at hindi siya, at pinakamalaking rank yung kaya niyong kuhanin, edi ito magiging masasagad yan. Either equal yan sa M or equal yan sa N. Kailan yan magiging equal sa N? Kung kunyari yung dito, saan yan? Kung dito sa situation na to, ang best case scenario natin is puno ito. So, ang rank natin ay equal sa M. Of course, yung kabilang situation is kapag nakatayo yung shape ng matrix. So, you see, nag-a-apply yung mga rules natin kahit ano pa yan. Kung M by N na nakatayo, mas marami yung M kesa kay N. Tapos, ano ka rin, puno rin yung rank as much as possible. So, ang mangyayari dyan is magda-diagonal ka pa rin dito. Itong ilalim yung puro zero. And kung R is equal to N, then puno itong diagonal na ito. Okay? So, can you see hands? Sorry for that, like, kind of long discussion. But are you okay with that so far? Okay naman daw? May questions pa? Can you send a chat if you have some? Okay, let's go straight to an example here. Let's do a short break, maybe mga 5 minutes. Then when I come back, like, think about questions about this. Like, kung meron kayong tanong on how to solve whatsoever, whatever. Then let's see what happens. I'll pause this recording. I'll resume recording now. Teka, sarado to. Search ko lang mo. Oh, Got it. Okay. Nakita niyo ba ngayon yung oh, anong nangyari? What? Anyway, nakita niyo ngayon yung ano, good notes? Okay daw? Yes. All right. So now, how do we answer this? Well, teka, bakit? Okay, let's go back here. So, paano niyo malalaman kung alin yung singular values? Well, wala pa tayong, di ba? We're not even decomposing a matrix. You just have to look at um how it's written and maybe figure out like ano kaya yung kanyang form, di ba? Oh, by the way, I used a square matrix here as an example, but this should work even for non-square matrices. And yung una nyong ma-recognize dapat dito is that the form looks like yung pinakadulo, it's diagonal, and may terms siya sa main diagonal. Okay? And it kind of looks like an eigenvalue matrix. And let's leave it that for now. Diba? Now, yung katabi niyang matrix, it looks like, okay, this is a matrix. But very important itong nakikita niyo ditong 1 over square root of 10. Because the 1 over square root of 10, it kind of normalizes yung column na ito at itong column na ito. You see? Diba? Ang magnitude nito ay square root of 10. And so, if you divide it by square root of 10, it normalizes the magnitude. And another thing that you'll notice is that these two columns are orthogonal. Like if you do an inner product of these two columns, you'll get 0. Likewise, ganun rin dito. And this 1 over square root of 2 also normalizes the thing. So, how does it look like? It looks like this. Is that what you got? Like, is that what you thought of? Can I see hands? If you're able to relate it to this form? Okay lang kung hindi. I mean, no shame. I'd like to know, honestly, kung sino yung nakaisip na it looks like it's AV is equal to U sigma. Hands, please. Yes daw? Yung iba? Go on. Hindi daw? Okay. But hopefully it is clear now kung bakit it kind of conforms to an equation of this form. Yung iba? Hindi sumasagot yung iba. Hindi rin daw? Okay. Okay lang. No problem there. Yep. I mean, at least now you know. Like, those are the things that you'll check. Like, when you see a product of two matrices, siguro yung naging, ano dito, yung naging um, additional source of confusion is yung number na nasa gitna ng dalawang matrix. Right? It looks misplaced. Like, why is it there? Blah, blah, blah. But really, any number that you place in between matrices or even outside matrices, you just multiply it, diba? Because it's a scalar multiple. So, yun yung mahirap siguro na ma-figure out na, oo nga no, kapag dinikit ko nga to dito sa matrix na to, it looks like this matrix as a whole is orthonormal. And that's one of the requirements for V, because all of the columns of V must be normal and columns of V must be orthogonal to each other. Likewise, ganun rin kay U. Okay? Anyway, ang sagot dito, once you figure out that it actually looks like this and it conforms to the requirements of V and U, then it is guaranteed that this is some kind of a set of singular vectors and singular values. So ito yung singular values natin. And ang corresponding left and right singular vectors nila, ang left singular vector na corresponding kay 3 square root of 5 is si 1 over square root of 10, 3 over square root of 10. And a corresponding right singular vector to that is 1 over square root of 2, 1 over square root of 2. Is that clear? Can I see hands if it is clear na yun yung answers natin dito? Okay. 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 All right. Now, swerte tayo dito dahil actually ano siya, full rank, di ba? 2 by 2 na nga yung matrix tapos puno pa yung ating singular vectors. So this is full rank. Like M is equal to 2, N is equal to 2, R is equal to 2. Okay. It could happen that one of these is 0. Like kunyari ito is 0, that means it's not full rank and it's coming from the null space, yung mga makukuha yung vectors. Okay. Here goes. Sorry. Napakita ko na kagad to, but here goes. Diba? Sabi natin, let's focus on this. Sabi natin, lahat ng columns of V are orthogonal to each other and that unit vector sila lahat. Ganun rin kay U. So what that means is that V inverse is equal to V transpose, U inverse is equal to U transpose. Very important fact about orthogonal, or rather, orthonormal matrices is this. And what it means is that if we multiply this on the right-hand side, no? If we multiply some kind of V transpose here, okay, is that it will lead you to a nice result, essentially. Okay? So, multiply nyo dun sa right side, V transpose. Like, so, kunyari, bigyan ko kayong example. So, let's suppose, again, V is always going to be squared, diba? V is always going to be in R M by M. Sorry. N by N. Okay? And so, like, if you have something like 1, 0, 0, and then 0, -1, 0, and perhaps yung, say, pinakahuli ay 0, 0, 1. So this is an orthogonal set. Like, if you multiply mo yan by its transpose, you can immediately see that ang transpose niya is itself. So you perform this matrix multiplication, you end up with an identity matrix here. Okay. All right. Okay. So it's really like saying that for these matrices, there exists yung inverse nila. Okay. So we will be sure that they're going to be invertible. And that if we right multiply yung V inverse na yan dun sa equation, you'll also do that dun sa kabila. So you will have U, sigma, and then V inverse. But we know that this V inverse really, since V is orthonormal, it's just V transpose. And this is it. Like once you've reached this, it's like saying that A can be decomposed into matrix U times matrix sigma and times matrix V transpose. That's it. That is its decomposition. This is what we call the singular value decomposition of the matrix. And any matrix has this, as in any matrix. And you can get a lot from this decomposition. Malalaman mo yung rank because you'll see if like kung alin maliit dun sa M tsaka N, you'll see how many items here are filled, right? And so on and so forth. Okay. Now, yung susunod na important aspect nito is that yung kapag ininterpret mo how this works, how this equation works, really, or kapag inattach mo sa sigma, okay? So yung elements sa sigma, inattach mo dun sa isa sa mga um, like vectors. 'Di ba? Alam natin na si U, bigay natin yung example for to make it simple, no? Let's make it A is in n by n. Para square lang, okay? And then let's make R be less than n, just to make sure that you will understand this decomposition even if hindi siya like best rank possible. Now what will happen is, let's say n is equal to 3. So sabihin natin n is equal to 3, so this is 3 by 3. Okay? And then R is equal to kunyari 2. So this is 2 is less than 3. So this is R. Ano magiging itsura ng mga matrices? So since 3 by 3 siya, yung U na matrix mo will really just be U1, U2, U3. So mga nakatayo yan na vectors, right? And then what will happen is you will multiply it with sigma. So remember you have sigma sa gitna. But since square nga si A, magiging square rin si sigma. Kasi kung ano lang yung shape ni A, yun lang rin naman yung magiging shape ni sigma. And then magko-conform lang yung shapes ni U tsaka V. But what's important here, so let me grab this para I have more space. So what's important here to recognize is that your sigma matrix will look like this. It will be sigma 1 on the first item in the diagonal, sigma 2. And then since the rank is 2, that means the last sigma that you get is 0. Okay. And then of course this is 0, 0, 0, this is 0, 0, 0. Itlog yan lahat. And then the V is going to be V transpose. So the V transpose is here. So you have V1 na nakahiga, di ba? V2 na nakahiga, right? Nakahigang version. So lagyan natin ng transpose. And V3 nakahiga din. Right? Now, tingnan nyo yung nangyayari dito. Hindi ba kapag ginawa ko tong transformation na to, it really is like saying na, like think about it. Parang block matrices na to eh. 'Di ba? Parang block vectors to na kinoncatenate. Ito rin, block vectors na kinoncatenate. So you can treat this as one whole unit, one whole unit, one whole unit. When you perform this multiplication, it really just makes sense to do some kind of inner product to make things simple. So you see what happens when you do that inner product. So ang mangyayari sa inner product is this vector now becomes sigma 1 v1 transpose, right? The next vector becomes sigma 2 V2 transpose. And the last one becomes 0, like 0 times V3. So it really doesn't matter what it will not contribute in any way to the remaining result, because this is what's going to happen. Now look at this. The left, what remains on the left side of this equation, or this like series of matrix multiplications, is that U1 is here, U2 is here, and then U3 is here. And in fact, even if you do another, so this is just gonna be one run of inner product kasi unit na nga yan, you'll end up with what we call the column picture, because the equations will be reminiscent of a column picture equation. Remember yung column picture of a matrix multiplication? Like instead of doing element by element and then all of those are inner products, what actually happens is that the matrix product is a sum of outer products. And the outer products are going to look like this. This is an outer product, U1, sigma 1, V1 transpose. Ginigitna ko na lang muna si sigma 1 just to remind you of the form, to inculcate the form to you na it is really U S or sigma times V transpose. And throuple sila, essentially. And then you have here plus U2, sigma 2, and then V2 transpose. And finally, we have U3, this 0. So this is a multiplier of 0 times V3 transpose. And as you can see, this is essentially a sum of outer products. And remember, this is rank 1. Bakit to rank 1? Because this is an outer product. Any outer product is a rank 1 matrix. And it will just follow the dimensionality. Like this is dimension, like the number of elements of U is 2. Sorry, 3 for this example. And the number of elements of V na nakahiga, di ba? Kasi V transpose yan, is 3 as well. So what we will have is a rank 1 3 by 3 matrix, right? That's it. And it's just saying that you're adding it to another rank 1 3 by 3 matrix. And ito rin. But you see, this has 0 singular value, so it doesn't contribute. So what I'm claiming here is that any matrix, really, once you think about its singular value decomposition, it is really a sum of R matrices. And these matrices are formed via the outer products and scaled by the singular values. That's the important part here. And this is until the rank. So dito sa example natin, it is until rank 2, so up until 2. And then the remaining is not contributing anymore. And this is a very big point of our discussion here, because seeing it this way doesn't give it justice. Na parang, okay, so para lang siyang x lambda x inverse, right? But seeing it in this form actually elicits yung very important properties niya. Na in fact, one of the things that should come to mind is if the singular values are ordered this way, like this is from sigma 1 up until sigma r, and sigma 1 is taken as the largest singular value that you got, then what that means is as you go through this sum, it gets less and less important. Because for instance, if your sigma 1 is 1000, and let's say your sigma r is 0.001, ano pang magagawa nung term na to dun sa matrix mo? Like, its contribution will be meager as compared to the largest contribution of this first rank 1 matrix. And anyway, this is really just I want you to do this after our class. Really just the same example as before. And then I want you to show me na yung A, again, the A there is this term here, this 3045. I want you to show me that, it is indeed gonna be like pag in-execute mo itong product na to, which is you're gonna put U, this is U, di ba? And then sigma, which is here. And then you put V transpose. Don't forget the 1 over square root of 2. You will have to include that here. Then you transpose it. I want you to show me that when you go through this series of this couple of matrix multiplications, you'll get this matrix here. Just to prove that this is indeed a singular value decomposition. And then likewise, I want you to show me the decomposition. Like, what are the rank 1 matrices? So you'll have to worry about U1 and then V1 transpose. Diba? And then what is its sigma? That is 3 square root of 5. And then so on. And the takeaway here is that once you've performed singular value decomposition, really, it all boils down to this. The larger the singular value is, the more important the singular vectors are in the matrix. Like, you can leave out yung mga contributions ng mga singular vectors na maliit lang yung singular value. Like, your matrix will not change a lot by leaving them out. That's what we have here. And that concept is central to yung binabanggit ko kanina na we don't even care about the 28 times 28, which is 784. We don't even care about the 784 individual pixel magnitudes. What we care about is a pattern that is inherent in those pixel magnitudes. Like, if you have a number 1 there na dun sa actual na image, then there must be some pattern, right? Pag nilista mo lahat ng pixel magnitudes niya, may mga 255 ka, may mga 0 ka na sunod-sunod, and so on and so forth. And that pattern itself, I don't know, it could be part of the singular vectors. Uh Yeah, well, not quite. It's not as simple as that. It's the rank. By the way, the rank of that data set, really, once you apply yung concept na to, and you are able to the next thing that I'll discuss shortly is gonna talk about that. Once you apply that, if I remember correctly, the actual rank na useful for the data set ng MNIST is up to about 50, I think, which is still much less than 784, meaning our brains are gonna look for 50 different patterns and then immediately say na, okay, that's a number 2, or versus that's a number 3. Okay, can I see hands? Are you okay with this explanation about the outer product and how it relates to the actual decomposition? Okay daw? Okay. Yung iba? Yep. Okay. Now, meron tong reduced form. 'Di ba naalala niyo kanina na we list all the singular values up until the rank, and then the rest of the diagonal is 0, and then you have zeros here, you have zeros here. Like, in fact, nothing bad will happen if you write a reduced version of this. Meaning, why don't you throw away yung mga columns na zeros dito sa sigma, and yung mga rows na zeros dito sa sigma? Meaning, instead of writing it as m by n, why don't you write it as r by r? So that's what we call by sigma sub r. That also means truncating the matrices formed by u's and formed by v's. Meaning, dito, putulin natin hanggang ur. Like, let's remove the rest hanggang m. Ganun rin dito, putulan natin yung R. Even though, of course, magiging non-square na si U kasi you see, what happens there is that U1 hanggang UR, ang parang height niyan, di ba? Ang height nitong matrix nito is M kasi M by M ito, itong matrix. So, mababawasan yung kanyang width. So, hindi na siya square. But, magiging square yung inyong sigma matrix. So, that's the trade-off there. So, hindi na square si V matrix, hindi na square si U matrix, itong si U sub bar and then si V sub bar, but they are gonna look nicer. And in fact, in implementations, if you are really gonna use this decomposition, this SVD, if your matrix is very large, kunyari 1 million by 1 billion, okay? Would it make sense to store those matrices? Like, kung 1 million by 1 billion, then that means your right singular vector, yung mga V's mo, will give you a 1 billion by 1 billion matrix, which is a pain in the ass to store. So in practice, we really end up doing this reduced version. Like, we only store the vectors that are relevant. Like, we throw away yung mga vectors na galing sa null spaces. Okay? Again, in practice, like, if you're gonna use this as a tool to perform yung mamaya yung discuss kong technique that allows us to perform yung mga analysis na binanggit ko kanina about thinking about um patterns. Yeah. We only store these things. Okay. Take note na pag nandito ka sa form na to, you have to be careful kasi hindi na magiging totoo na, you see, V transpose kanina nakita ninyo, 'di ba? V transpose led to identity matrix. Siyempre, sa form na to, hindi na mangyayari 'yon. Very important. Bakit siya hindi na mangyayari? Kasi tinuncate mo yung V matrix. Hindi na magtutugma na squish to identity matrix yung product na to. Pero yung other way around, V transpose V, it's still gonna give you identity. U transpose U is still gonna give you identity because again, these two definitions are actually like definition siya ng dot product, di ba? Unahin mo yung transpose bago yung actual. Pero ito, hindi kasi ito definition ng dot product and it's only true if V was square and if U was square. Okay? Now, sorry na-spoil kayo. Mali yung nalagay kong animation. Pero na-spoil na kayo eh. Na actually, yung left and singular vectors, sa totoo lang, eigenvectors lang rin sila. Ng ano daw. So, you'll see shortly. Doon nagiging important yung A transpose A. So, di ba sinabi ko kanina, important yung um, property na pag ginawa mo tong A transpose A, then it is at least positive semi-definite. Not guaranteed na positive definite, but it is at least positive semi-definite. Now, ganun rin si A transpose, A transpose, I mean. Kasi si A transpose, di ba, pwede mo rin namang imaginein yan as pinalitan mo lang si A ng A transpose. That's it. So, it still applies, like this rule still applies to it. The point here is both of these, okay? Both of these matrices are gonna lead to, both of these products are gonna lead to symmetric matrices. They're gonna be a little bit different. Not a little bit actually, but they're really gonna be different. Kasi yung isa dyan ay M by M, yung isa dyan N by N. But the point is, yung eigenvalues nitong A transpose A or ni A transpose are all gonna be greater than or equal to 0. Kasi nga, guaranteed yan na positive semi-definite. Okay? Now, what's the point of this? Well, naalala nyo yung sa eigendecomposition na sa totoo lang, S is really some orthonormal matrix Q times lambda matrix and then matrix Q transpose. Ito yung magic dito. What if palitan nyo si A, no? Palitan nyo si A nung kanyang singular value decomposition. Kasi nasabi na natin kanina na it always exists for any matrix A. The singular value decomposition is U S V transpose. So why don't you put that here? So palitan nyo yung A na to, palitan nyo yung A na to. May magic na mangyayari dito sa expression na to. Likewise, ganun din dito sa expression na to. You see, what will happen is that A transpose A is really gonna be like this. Let me show you why. Again, we're starting with, we want to replace A transpose A by its singular value decomposition. So you have U, you have sigma, you have V transpose. That is its singular value decomposition. And you have transpose here, right? And then A can also be replaced by U, sigma, and then V transpose. Okay? All right. Now here's the trick. Here's the trick. Like, naalala niyo yung property ng transpose na if you have A and B and then you do a transpose, what's gonna happen is it's gonna be B transpose A. It's gonna be B transpose times A transpose. Like, why don't you group this and ito, just gawin mo yun. So if you do that, you're gonna end up with V kasi mawawala, ma-undo yung kanyang transpose. And then you're gonna have U sigma transpose, right? And then apply that property again. So you're gonna end up with sigma U, sigma transpose U transpose. Nakikita nyo na yung magic? Sulat nyo lang rin ito. Ano yung magic dyan? Ano ulit si U? U is orthonormal, like V is orthonormal. So this becomes identity. And you'll be left with this. What's so special about this? Well, ano bang itsura nitong sigma transpose times sigma transpose times sigma? Well, bigyan ko ng example. Kunyari, sigma is ganito yung itsura. Sigma 1, sigma 2, and then 0, 0. Again, this could happen. If the matrix is 2 by 3, this could happen. Ang rank niya ay 2. So may values yan. Right? So ano yung itsura ng sigma transpose? So again, this is sigma. Okay? Ang itsura ng sigma transpose is just patayuin nyo lang yung matrix na yan. Okay? So this is sigma transpose. What if we multiply it with sigma? So what the sigma is this one here. Again, this is sigma. So you see, what are you going to end up with? Well, what you're going to end up with is, so pag in-inner product nyo yan, magiging sigma 1 squared. Pag in-inner product nyo to, wala. Pag in-inner product nyo to, wala. Right? Inner product nyo to, wala. Inner product nyo to, sigma 2 squared. Inner product nyo to, wala. Lalo na pag nag-inner product ka na dito, wala, wala, wala. Ang magiging itsura nitong matrix na to is this. Tan, tararan. Well, paano yung kabaligtaran niya? Actually, gagana rin to kung gawin niyo yung AA transpose eh. Yung kabaligtaran niya, I'm not gonna show you how it happens, but if this is sigma, or at least for this example, this is sigma transpose times sigma, ang sigma times sigma transpose that will arise in the other way around is gonna be like this. Dito naman sa space na to ay full rank. I mean, yeah. Magiging, yeah. So, takeaway. Anong itsura nito? This is really like some what? The sigma transpose M sigma is guaranteed to be, I mean, the eigenvalues of that, I mean, the eigenvalues of A transpose A are gonna be the diagonals nito. And as you can see, for this example specifically, positive ito, sure. Oops. Yeah. Positive ito, sure yan. Positive ito kasi square, di ba? Ito ay 0. So that is positive semi-indefinite. See? And ano tong V tsaka V transpose sa gilid? Eh di ba kasabi lang natin kanina na si V is an orthonormal matrix? Eh di ba yun rin yung requirement ng spectral theorem that if you have a symmetric matrix, it is guaranteed that the matrix composed of its eigenvectors is gonna be orthonormal. Like normalized yung mga eigenvectors. So ito rin yun. Ganun rin dito. It's the same form. It's just gonna be a different matrix yung nasa gitna. Like yung matrix nito is 2 by 2 na, no? Likewise, U is 2 by 2, U transpose is 2 by 2. Dito naman, V is 3 by 3, V transpose is 3 by 3. So actually, yung V, they are the eigenvectors of A transpose A. And yung U, sila ay eigenvectors ni A transpose. Isn't it cool? Can I see hands if you're okay with this? Like you understood what happened? And yung profound implication nito. Now there is a relationship between eigenvectors and left and right singular vectors. You just have to do this thing if you want. Okay. So just to summarize, this is it. All right. And this is it. So, well, let me tell you something. This still doesn't tell us how to solve for the SVD. I mean, you can go ahead and use these definitions. I mean, that's probably the most straightforward, I would say, brute force way of getting the decomposition. How? Well, first of all, why don't you do this? Why don't you do A transpose A? And then once you get the A transpose A, why don't you get its eigenvectors and eigenvalues? Because by then, you'll be able to get yung kanyang singular values, well, yung squares ng mga singular values, and also the right singular vectors. But you're not yet done. You still haven't arrived here dahil ang alam mo lang is si sigma at si V. The next step really is to do this as well, and then, well, alam mo na kagad dapat yung kanyang magiging singular values, magiging eigenvalues, kasi dapat parehas lang dun sa kanina. So, mas madali ito na process. Kasi since alam mo na kagad yung eigenvalues, you can just go ahead and solve for the eigenvectors. But still, it is kind of, too much work. A better way of doing this, really, is to do one of the two. And then, hindi nyo na gagawin yung sa kabila. Hindi nyo na gagawin ng eigenvalue decomposition yung kabila. And ito pa yung trick. it's not necessarily good na si A transpose A yung gawin ninyo because sometimes yung better way to decide kung which one to do, kung A transpose A or A transpose, is to see ano yung magiging dimensions once you're done with this. Kasi kunyari, dito, tinan nyo to. Um, kung ito yung lumabas sa sigma transpose sigma, what that means is that 3 by 3 yung lalabas kay A transpose A. While kay A transpose, ang lalabas ay 2 by 2. In this case, ang clear na dapat ninyong gawin really is unahin yung magkakaroon ka ng 2 by 2. Bakit? Kasi madali gawin yung eigenvalue decomposition nito or eigen decomposition. The smaller the dimensions are of the matrix, like whether it's A transpose A or A transpose, the easier it is to get the eigenvalues and eigenvectors. Okay, easier and faster. I mean, not only manually, but also computationally. It is going to be faster. Now, let's suppose nga ito yung magbibigay sa inyo nung mas maliit na square matrix. Okay, go ahead, be done with that. Now, your next step really is gonna be like make sure that V is orthogonal. Very important part. Bakit? Kasi it could happen na meron ka palang makukuha ditong zero eigenvalues. You see, it's not guaranteed that all of the eigenvalues here, kahit na siya yung mas maliit, no? It's not guaranteed na ganito yung mangyayari. Ganito. Because mangyayari lang ito kapag R is equal to M. Di ba? Tsaka lang siya mangyayari. If R is equal to M. But R can be less than M. So, it could happen na mawala ito, maging 0, di ba? So, you see, there still remains the task yung tinatawag na orthogonalization. So, naalala nyo pa naman yun sana, hopefully, like the Gram-Schmidt orthogonalization. Like, what you're gonna end up here with is the list of vectors, list of eigenvectors that correspond to yung eigenvalue na ano, na ito. Pero, kung kunyari, nakuha mo na, yung the rest of the eigenvalues are 0, then, why don't you just orthogonalize? Like, alam mo na yung set of eigenvectors na non-zero si sigma, then you just build the remaining vectors from it. Kasi ang magiging requirement lang naman is the preceding vectors must be orthogonal to all. Diba? So, yeah. Next is, ito yung kinaganda nung kapag binalikan ninyo yung concept or yung truth, I would say, that you are getting a throuple out of it. Meaning, for every V sub k, for every sigma sub k, you have a U sub k. So, you can compute for U sub k this way. As in, mabilis lang to na matrix multiplication and then division by a scalar. But this is only gonna be true for all of k is equal to 1 to r. Meaning, there will be U sub k's that you won't get from this. Yun nga, kapag, lalo na kapag since inuna mo nga yung case na mas maliit yung size na makukuha mo for the eigen decomposition, what that means is sobrang dami mo pang mga use na hindi makukuha kasi hindi mo pa makukompleto yung dimension M. So, pupunuin mo pa yon. Again, also through orthogonalization. Ito yun. Tadyan! Yep. Sorry. Pwede pa lang ihuli mo. Like, you don't need to do the orthogonalization here. Probably what I meant here when I wrote this was just that make sure na you've done the eigen decomposition properly because if V here, like the one you get here, is not orthogonal, then you made a mistake somewhere. Okay. All right. And actually, I was supposed to ask you how you guarantee that U is orthogonal, like when you do this algorithm, but um, I won't demonstrate it now. It relies on really like uh doing this like um like if you know that V sub 1 is orthogonal to V sub 2, like you will also guarantee that U sub 1 is orthogonal to U sub 2. Okay? Ano yan? Mag-inner product ka. Yeah. Okay. Now, I have an exercise here, but really you've already done this. I mean, you've seen the answers to this, but I want you to do it by going through the steps. Okay. So make sure you are able to demonstrate it with this example before you do the assignment, because I'll give an assignment na siguro non-square and so on and so forth. So once you've done this with a square matrix, you'll probably be ready with non-square matrices and do the other steps like this, yung getting the orthonormal basis. Now, I've also written here some frequently asked questions from like from previous semesters, like if A is symmetric in the first place, diba? Is symmetric and positive definite. Ano yung lalabas sa kanyang SVD? Well, ang sagot dito is something really close to the eigenvalue decomposition or from the eigen decomposition. Okay? Um, and by the way, if it is symmetric positive definite, then that means all of the eigenvalues of A transpose, sorry, all of the eigenvalues of A are positive, right? And if that is true, all of the eigenvalues of A are positive, then what's gonna happen is that lahat ng mga eigenvectors ni A, yun na din yung left and right singular vectors mo. As in, equivalent sila. Like, really, you'll be able to show that indeed U is equal to V for in that case. And this is rare because this only happens when the matrix is square, and it only happens when the matrix is symmetric positive definite. Now, paano kung symmetric siya pero may, let's say, negative eigenvalue ka or negative eigenvalues? Marami. Actually, yung makikita nyo ditong cool is that pag negative yung kanyang eigenvalue, then that means, di ba, naalala nyo yung um, nagiging rule natin for A and its singular value decomposition, na yung sigma is gonna be composed of, kunyari, ganyan. So, symmetric matrix, so let's say 2 by 2, and ito yung lumabas na sigma. Both, um, both sigma 1 and sigma 2 are gonna be greater than 0. Okay? Guaranteed yun. Meaning, positive yung lahat ng mga singular values. Now, how does that translate to the concept of negative eigenvalues? Well, ang mangyayari lang doon is to elicit some kind of negative eigenvalue. What will happen at positive yung singular value na lang kukuha mo? What will happen kay A is yung eigenvalue niya, kunyari, let's say eigenvalue 2 is negative, like negative to nung sigma 2. The only way to elicit this is to have yung U tsaka yung V not equal to each other, but rather one is the negative of the other. So for example, one of the u's, let's say, is 1 over square root of 2 and negative 1 over square root of 2. Kung yan yung kanyang u. Pag minultiply mo yan sa, you see, pag minultiply mo yan sa sigma 2, dapat ang V niya, and by the way, if this is corresponding to a lambda, again, this matrix is square, so it can have eigenvalues. Kung ang corresponding niyan na lambda, again, also again satisfies this relationship, what's gonna happen is for this lambda, its eigenvector is 1. I don't know why this keeps happening. Its eigenvector, it could be 1 over square root of 2 and minus 1 over square root of 2. And so since eigenvector yan din yung nakahiga dito, 1 over square root of 2 and then minus 1 over square root of 2, diba? But, you see, since this is negative at bawal maging negative si sigma, what's gonna happen dito sa kabila is yung corresponding V ni U na ito, instead of them being equal at nakahiga lang yung isa, mangyayari dito is ito tsaka yung nandito ay negatives of each other. So what will happen here is that this is gonna be minus 1 over square root of 2 and the other term is gonna be plus 1 over square root of 2. That's what's gonna happen. Hindi magiging equal yung U tsaka yung V mo, but rather negatives of each other. Kasi kailangan nga ma-preserve yung fact that the singular values are always positive. Okay. And finally, if A is orthogonal in the first place, then its singular values are equal to 1. And this is rather easy to prove. Really, it's just like well, kung orthogonal na siya at supposedly ma-decompose mo siya into U sigma V transpose, well, orthogonal naman ito, di ba? Like, you can write it like A is equal to U, di ba? Kasi ito orthogonal or orthonormal pala yung term natin sa class na to. Meaning, normal yung lahat ng vectors at orthogonal sila sa isa't isa. So you can set A is equal to U, and then sigma must be identity matrix, and then V transpose must be identity matrix. Right? Or you can set A is equal to V transpose, whatever A is, and then U must be identity matrix and sigma must be identity matrix. Whichever the case it may be, sigma will always need to be the identity matrix. So what that means is all singular values equal to 1. Okay? Yeah, can I see hands here? Like, if you're okay with this process and ready to solve assignment. Okay. Sige. All right. Now, as my last point for tonight, let's go back dun sa idea ng, di ba, binanggit ko kanina yung outer product. It really is gonna be an outer product if you think about it. Let's go back to that idea. If you truncate it, like, di ba dapat hanggang R yan? R is the rank. If you truncate that sum, okay, what you're getting is what we call the closest rank K matrix to A. Meaning, given that the rank is K, AK is approximately equal to A. Approximately because K is less than R, where R is the rank. If K is equal to R, then that you're just saying a tautology. A is equal to A. Kasi nga, yun na yung full decomposition. But again, if you truncate it, like tinanggal mo lang yung last few parts, and then you're left with this item, what we call that is the closest And you see the notion of closeness, it really relies on the concept of norms, right? So later in this slide I will discuss a few norms, but that's not the point here. The point here is that you can approximate A using a lower rank matrix. That really is the point. And this is the basis of principal component analysis, which we will discuss. Will part of your midterm, which is an unsupervised learning algorithm. So the first unsupervised learning algorithm you've learned is k-means, right? So now principal component analysis really is based on singular value decomposition, and its main purpose is to extract the most important k-dimensional subspace. So when you say k-dimensional subspace, it's like saying that if you live in R2, the most important two-dimensional subspace is R2 itself, right? Kasi nga, nasa R2 ka na eh. Pero could there be a one-dimensional subspace that is, I mean, the most important one? Kasi it will let you approximate what is happening in the data. So naalala nyo yung very, very first point natin. Let's go back here. This one here? Yes, this is in R2. But, it looks like rather interesting yung data. Nasa R2 siya, pero yung data mo, since ang dami mong examples, it really is represented by a matrix that is, let's say, sabihin natin for this example, let's say 30 by 2, where 2 is the number of features. But it looks like if you grab this subspace, and what is this subspace? Nasa R2 ka, di ba? If you grab this subspace, this is a one-dimensional subspace, which is very, very, like, I mean, it's not only analogous, but what we're doing right now really is what uh is the point that I was making in the final slide that I was showing you. This is really like a k-dimensional subspace where k is equal to 1, which is k is less than r. Ang rank nitong matrix representing this data set is 2. Let's say, yun nga, rank 2 siya, like full rank. Not full rank, but best rank that it can have. But if you confine everything, like if you just looked at this line here and then you forgot about R2, you still get a lot of information there. Like this point is gonna be this point here. This point is gonna be this point here. This point is gonna be this point. This point, gonna be this point, gonna be this point, gonna be this point. Lahat yan mapupunta, magko-collapse, papunta dun sa line. But isn't it nice to say na, this is still far from this? You're able to say that pa rin. Even if you're living in this subspace and not on the two-dimensional space. Granted, you lose the nuance provided by these distances from the line, right? May nuance yan eh. But if you ask me, depending on my purpose, baka okay nang nandito lang ako sa line na to tumitingin. And that really is the point of principal component analysis. Like if you've encountered principal component analysis in some statistics class before, you've probably talked about concepts of variance and how what it means, like getting the axis of maximum variance. Essentially, when you do SVD, you're doing just that, especially when you're ordering the singular values from largest to smallest. It's like saying that the smaller the singular values are, the less important, no? The less important those directions are. Okay? And yeah, this is what we're gonna talk about next week. where I will detail yung principal component analysis. But first, I'll review you about this concept because you might forget it next week. I'll tell you about yung theoretical basis nito, so that confident tayo na when you do truncate it, like when you do list all of the terms, and then you do cut it at some point, you're still getting the best deal. And this really is the idea behind yung sinasabi ko sa inyo kanina na even if you had 784 pixels to look at, what you really care about is a low dimensional substance, maybe up to 50 dimensions. Your eye, you yourself as an intelligent individual is not looking at each pixel. Are you doing that? You're not doing that. You're not looking at each pixel and then telling your brain what the numbers are. What you're doing is look at the picture as a whole, do your principal component analysis, and then leave the first 50 ones, the first 50 dimensions in that subspace, like a really smaller dimension, really smaller space than the original space, and then conclude something about it. That this is number one, this is number five. It is amazing. Our brains can do that. And that is one of the thrusts of, like doing this machine learning, and later on like AI, is that one of the most important parts of machine learning. It really is dimensionality reduction here, this one, because that allows you to make conclusions about the data with just a smaller dimensional subspace. So yeah, I'll end here. Apologies for the overtime. I hope you enjoyed the class. I'll see you next week.